The next detail to examine regarding the law of universal gravitation is capital G, the first time that it was measured. As I previously have mentioned, capital G wasn't measured until well after Newton's death. Newton died in 1732. Ultimately, the measurement of G didn't occur until about 60 years later. The measurement of G, the first time it was performed by an Englishman named Henry Cavendish. It was in the 1790s, and his experiment is referred to as the Cavendish Experiment. Okay, so the measurement of capital G, the universal gravitational constant. This is now the 1790s. This is what is called the Cavendish Experiment. Okay, the Cavendish Experiment uses a specific type of pendulum. It's called a torsion pendulum. Let me draw what the pendulum looks like, and then I have a simple demonstration of an example of a torsion pendulum. Okay, what Cavendish did, and he did the experiment, by the way, on a pretty large scale, is he hung an iron bar like so. Here's the bar from a wire. So the ceiling is up here. And then on the iron bar itself, he mounted two masses. There's a mass here and a mass here like so, and each of the masses are labeled as M. These are experimental controls. Okay, the bar itself, hanging like so from the ceiling, could ultimately then swivel horizontally like this. This type of pendulum, as I said, is referred to as a torsion pendulum. I have a simple example of one over here. Let me tilt my phone. All right, so tilting my phone here off to the side. Like so. So on this hanger right here, I have a plastic bar like so, and I have it arranged as a torsion pendulum. Ultimately, it can swivel horizontally like so. Once again, this type of a pendulum is referred to as a torsion pendulum. I'll be referring to this demonstration specifically, by the way, later in this year when I describe to you the electric force. But for now, let me go ahead and tilt the camera back. Like so. Okay, now getting back to the actual Cavendish experiment. Okay, right here we'll say is the floor, like so. And then off to the side, on the floor, Cavendish places identical masses. I'll call them capital M and capital M, like so. Now this is what the experiment looks like when you look at it from the side in profile. So this is a side view. Okay, here's what the experiment, however, looks like from the top. So imagine being on a ceiling and then looking down on the experiment. So now here's the top view. Okay, so first of all, we have the wire itself hanging from this point, and then we've got our iron bar like so hanging from the wire. Okay, and then we have the two masses in blue, small m like so, attached to either end of the bar. And then we have the red masses, capital M, positioned on the floor. They're positioned in the following way. This right here, capital M, is positioned such that it's closer to this end of the pendulum than it is to this end. And then we place the other mass, capital M, over here, such that it's closer to this end of the pendulum than it is to this end of the pendulum. And then we just set this up and then let it go. And then what happens? Well, there is a very minute force of gravity exerted on this side of the pendulum due to this mass here. There is a very minute force of gravity exerted upon this side of the pendulum due to this mass here. Now, as I said, this mass is placed closer to this end of the bar, and this mass is placed closer to this end of the bar, such that ultimately the pendulum begins to swivel or oscillate in this direction. And then very slowly, so slowly you can't even see it move in real time, and I know because I've done the experiment, ultimately then the following happens. The torsion pendulum begins to swivel, like so. It then overshoots the masses, capital M, slows down and stops, comes back, overshoots the masses, capital M, slows down and stops, comes back, and so on. In other words, the pendulum begins to oscillate, but the amplitude or size of the oscillation decreases with time. So then therefore, after the course of several hours, the pendulum then oscillates like so, and it ends up then diagonally across from the masses like this. So right here is the initial position of the pendulum as I've drawn it already, and then the final position of the pendulum looks like this. The pendulum executes a specific type of motion that was well understood by the time of Cavendish called damped harmonic motion. We'll look at that type of motion, by the way, later this year. The pendulum executes what's called damped harmonic motion. The details of damped harmonic motion were well understood at the time, and you can use those details to calculate exactly how much force is being exerted upon the pendulum. Okay, now take a look at the law of universal gravitation. So if the motion of the pendulum can be used to calculate how much force is exerted on the pendulum, and then on the right-hand side of the equation, we have experimental controls. So for example, you already know, of course, what the relevant masses are. You set up the experiment. You also know what the relevant distances are. You set up the experiment. So what I have circled there in the expression, those are experimental controls. So if the motion of the pendulum can be used to calculate the force, and you know all of the stuff that I've circled, then the only thing that's unknown, of course, is capital G, which can be measured. So capital G can be determined. Okay, now because the motion of the pendulum itself is so slow, I can't demonstrate it to you here in the classroom. So then therefore what I've prepared for you in today's folder is a screencast of a video of the demonstration of the experiment being performed. Go ahead and take a look at that screencast now. There is, of course, an Edpuzzle associated with it.